Assalamu alaikum. I hope you guys are doing well and thank you for joining. Let's start. Today we'll be focusing on organic reactions. Uh, I would try कि हम maximum जितने भी reactions को एक दफ़ा review कर सकें. We'll do that because I want to move on to solving past paper questions. So without knowing the mechanisms, without knowing the basic concepts, we won't be able to do. This is supposed to be a comprehensive review of the organic reaction mechanisms. I will try not to go into the detail of the rate of reactions, which reacts faster, which reacts slower. It's simply the main mechanisms, which is usually a 2 or 3 mark question that examiners usually asks of the student. So I have your book here so that I know which reactions to focus on, just as my notes. But yeah, let's get started. Organic reactions, the first thing you need to know is about the kind of bonds that you have. So you have sigma bonds, so that's the first category. There's a sigma bond and there's the pi bond. Okay, the difference between these is that sigma is it is more, it's lengthy compared to pi. Pi is usually shorter, but we can't compare sigma and pi directly in a reaction. It's simply that when we do a reaction, we will always have the first bond will always be sigma, the second and third bond between any two atoms will be pi. So that's the first thing you need to know. That carbon and carbon, when they react, for example, the first bond that they have will be sigma. Similarly, let's suppose this carbon reacts with oxygen. The first bond that it makes is sigma. Now let's say the carbon on the left side, it reacts with hydrogen and gets 3 hydrogens. So all three of these are sigma, because the first bond between any two atoms is sigma. The second bond between any two atoms, for example, this one makes a new bond, so this one is going to be pi. The green one is sigma, the blue one is pi. Okay, now when they react, let's say I want to compare it with this bond, we cannot measure the bond energy of this pi bond alone, but we do know that this bond is weaker than this bond altogether. That's the second thing you need to know, that single bond obviously it's weaker than the double bond, but we cannot measure the bond energy of just the second bond in two atoms. We can measure the bond energy of the whole thing. That's the first thing you need to know. But we do understand that pi bond is relatively weaker and it's easier to break just the pi bond compared to just the sigma bond. So that's also something you need to know, that the energy required to break this bond altogether might be more than the energy required to break just this bond. So that's the second thing you need to know. Then what you need to know is कि जो हमारे पास ये जो double bond है, there is something in here that is not shown right now, which is how the electrons are arranged. So the sigma bond has electrons arranged right in this region between them. This is the region of overlap for orbital where the sigma bond is made. Of course, they have other things, but I'm not focusing on that. And the pi bond over here will be in this region. It could be top and bottom, or it could be front and back. It could be one of those. So if you have a third bond, it will be in the front of this area and the back of this area, but it will be just like these lobes. Why is this important? Because that shows us where the electrons are more likely to be found, where that area is where electrons can be found easily, which also means that if something comes here, then electrons will do two things. One, if something comes close to this area, then electrons will repel other electrons that it has. So for example, if I had a bromine atom that approached this one, this is part of one bromine molecule, and let's say this bromine atom came closer to this as the molecule is floating around, then this area, because it has electrons, will repel the electrons over here. So the electrons will go further away. It is just like in grade 10 when you studied electrostatic physics and electrostatics, when you study that. So they tell you that if you have a positive rod and something, let's say this was a positive rod, and if it came close to a metallic sphere, then the electrons on the other side will come close to it and this side will become positive. This is an induced charge. Just like that, if you had a metallic sphere and you brought a negative charge close to it, then the electrons on this side will go further away from it and this will become positive because of that. Okay, the charges are obviously equally distributed over here, But the point I'm trying to make here is that यहाँ पे जितने electrons होंगे they'll be pushed away. So वो दूर चले जाएंगे and you'll get slightly negative charges here and slightly positive charges here. That simply tells us that the electrons have been pushed away. Okay, so that is also something you need to know about the sigma and pi bonds. That when something comes close, a molecule comes close to it, it will get partial charges, and this is basically London force at play. Okay, so that is what we'll see, and they will attract each other because of that. Third thing you need to know is the concept of electrophile and nucleophile. Okay, so hold on, let me share the link. Okay, yeah. The third thing you need to know is about electrophiles and nucleophiles. Electrophiles are the ones that are attracted to the positive negative charges. Electrophiles हैं, ठीक है. So अब negative charges की तरफ कौन attract होगा? Something that has empty orbital, because electrophile means that it has an empty orbital and something might be interested in coming over there. Second, if it has a positive charge or it have a slightly positive charge. If one of these cases are there, then it will be an electrophile and a lone pair will be attracted to that, and that is how it will react. So if something has a positive charge, slightly positive charge, or an empty orbital, it is an electrophile. If something has a negative charge, or if it has a lone pair of its own, then it will be attracted towards the positive charge. Then it is a nucleophile. So electrophiles will always have they will always have empty orbital. They will have positive or slightly positive charge. Nucleophiles, on the other hand, will have lone pair, and they will have negative or partially negative charge. And that is how they react, and that is how they are able to approach one another. Yep. Okay, let's see. So now that we understand how these things work, so this is an electrophile, this is a nucleophile, let's try to get into the reactions that we have. Alright, so the first reaction that we have is free radical substitution. Free radical substitution will obviously occur if you get radicals. So how do you create radicals? That's the first step. And that step is called initiation. Okay, so initiation is where you start making those radicals. Now, radical is only possible if electrons are equally distributed when a bond breaks. So when you have a bond, I'll take chlorine as an example. So chlorine and this chlorine have a bond between them, and they are sharing an electron pair. So when this bond is broken, you can give both of these pairs to one atom and remove them from the other atom. It is possible. But to make a radical, free radical substitution, you want to give one of these electrons to this chlorine and one of these electrons to this chlorine. And that is why I've shown a curly arrow with just half a head. That simply means that this is one electron. If I made a complete curly arrow like this, that would mean a lone pair, two electrons gone. That's not happening here. It's just one electron to the right side, one electron to the left side. What that does is basically creates two radicals, and I'm showing them with this dot, and those are the two radicals that we made. So we need those radicals to get things started. Okay? Alright, so now that we have these radicals, what's next? These radicals will obviously approach some atom, some molecule, and now over there they can do what we call propagation. Okay, now I'm going to make a list of all the atoms that we have here. Let's say I start with ethane. So I have C2H6 and I have chlorine. These are molecules, they're stable molecules. But now during this reaction, I have created this radical. Can this radical react with chlorine? Yes, but it won't lead to anything. Can this radical react with this? Yes, let's do it. So we have C2H6. Let me draw it out. And the chlorine radical is approaching it. When that happens, this hydrogen can make a bond with this chlorine radical. And that is what will happen. This will create a bond with that, and you will get HCl. And whatever is left, that other thing will now have a radical here. What has happened is that this bond has broken. Because of that radical being there, this bond has broken. And now, basically, half of a pair comes here and half of a pair comes here. So this thing that happened here, it has been caused here because of this chlorine radical. And when that happens, they simply react with each other and you're able to get them into HCl. What happens to the other thing is simply just becomes a radical itself. Now this radical, wherever it goes and comes across a basic molecule, it can react with it. So for example, I have C2H5 radical created now. Now can it react with this? Yes. So if it does that, that will be called termination. Why? Because two radicals reacting together make stable molecule, and that is termination. So let's try that. So I have two radicals. When they react together, the thing becomes a stable molecule. Story khatam. You get this and you're done. But what if this were to react with a stable molecule itself, or if this were to react with another stable molecule like that? In that case, you will get another propagation reaction. So we will get this one, and this reacts with chlorine molecule, for example. So just like this chlorine radical was able to break this bond between carbon and a hydrogen, this radical will obviously break the bond between this chlorine. And now same thing happens here. So you get this radical joined with chlorine plus a chlorine radical. So we have created C2H5Cl, another chlorine radical, from the reaction of these two. So here's the thing what you need to know about it. If you keep track of what radicals you have, what molecules you have, then it's very easy to figure out what's happening. When we started, we had these two. To make radicals, we gave ultraviolet light to this, and that created radical. तो अब जो radical molecule से react करेगा तो propagation होगी, radical से react करेगा तो termination होगी, और molecule अकेला radical बनाएगा तो initiation होगी. So तीन ही तो cases हैं आपके पास, या radical molecule से बने initiation, radicals आपस में मिलके molecule बना दें stable molecule, that is termination, और अगर वो आपस में खेल रहे हैं then that is simply propagation. So ये propagation होती रहती है. Let's try one more. What if I had this one and I reacted it with this one? Possible है, बिल्कुल possible है. तो क्या होगा? ये वाला इससे हाइड्रोजन ले लेगा और आपको एक नया रेडिकल मिल जाएगा. Let me show you. We had C2H5Cl reacting with C2H5 radical. What will happen? It's going to create C2H5 radical, C2H4Cl radical, because एक हाइड्रोजन वो ले लेगा and C2H6 बन जाएगा हमारे पास. That is one possibility. What if I made this react with this one? Very likely. So क्या होगा? C2H5Cl reacting with another chlorine. What will it do? It will give it one hydrogen. So हमारे पास C2H4Cl radical बन जाएगा plus HCl molecule बन जाएगा. So this radical will then obviously it can react with the molecules, it can react with another radical to do termination reaction. But the point is, as long as you keep track of all the radicals that you have in your reaction container, all the molecules you have in your reaction container, then the steps can easily be figured out. If the step is moving another, creating another radical, that's the propagation step. If the step is leading to just a stable molecule, that's a termination step. If the step is starting from stable molecule and then making radical, then that is a initiation step. So अकेला molecule react कर रहे हैं, initiation. अकेले radicals react कर रहे हैं, termination. Radical and molecule both react कर रहे हैं, propagation. So just keep track of this, that what can react with what, and you'll know. Okay. So any questions on this? Please let me know. Assalamualaikum. Yep. All right. something's wrong. I don't know what that is. Anyways, let's move on to the next step. This reaction is the reaction of alkenes. So we have seen substitution, we have seen how that substitution reaction occurs and what is the mechanism there. Now we are going to look at addition, and that is obviously addition can be of electrophile, it can be of nucleophile. Free radical addition nahi humne dekhi. Okay, so how does this work? For addition, we will focus on alkenes, and as I've told you, alkenes have pi bond, and pi bond is what determines their reactions. So ये हमारे पास alkene है. I don't care what that other thing is, we are not focusing on that. हम सिर्फ देख रहे हैं हमारे pi bond को, और यहाँ पे जो pi bond है, this is characterized by this cloud of electrons that it has. What this cloud does is if something comes here और उसके पास अपने इलेक्ट्रॉन हैं तो ये उसके इलेक्ट्रॉन्स को रिपेल कर देगा, जिसकी वजह से उसके ऊपर स्लाइटली पॉजिटिव चार्ज बन जाएगा. एंड द मोमेंट समथिंग हैज अ स्लाइटली पॉजिटिव चार्ज, व्हाट इज इट? इट बिकम्स एन इलेक्ट्रोफाइल. ठीक है, तो यहाँ पर जैसे ही कोई नॉर्मल मॉलिक्यूल आएगा, दिस विल रिपेल इट्स इलेक्ट्रॉन्स और वो उसको इलेक्ट्रोफाइल बनाने की कोशिश करेगा. सो लेट्स ट्राई दिस विद सिंपल मॉलिक्यूल लाइक ब्रोमीन. सो दिस ब्रोमीन कम्स हियर. ये ब्रोमीन जैसे ही इसके क्लोज आएगा, द इलेक्ट्रॉन्स ऑन दिस ब्रोमीन विल बी रिपेल्ड. तो यहां पर जो इलेक्ट्रॉन्स हैं, दे विल रिपेल द इलेक्ट्रॉन्स हियर. And that will mean that this gets a slightly negative charge, this gets a slightly positive charge. Don't forget the slight charges, they get 1 mark. Now you have electrophile ready. पहले it was a normal molecule, वो electrophile नहीं था. Now your electrophile is ready. What will happen next? The moment these pi electrons, this cloud of electrons, sees a positive thing, it latches onto it. वो उसको attack करेगा फौरन. तो हमारे पास यहाँ से attack आएगा. Now one thing that you have to remember, even though this is called electrophilic addition, yeah. Even though this is the electrophile that is going to be added into this molecule, the arrow is still coming here from the molecule. Why is that? That is something that confuses some students. Remember, the curly arrows always tell you the movement of electrons. Assalamu alaikum, Saeed. The curly arrows always tell you movement of electron pairs or just one electron. They do not talk about how that what you have the molecule itself या वो क्या कर रहा है, उसकी ये बात बिल्कुल भी नहीं करते. It is always the electron that matters. Okay, so electrons or electron pairs, those are the ones shown by curly arrows. तो यहाँ पे ये electrons ही उधर को attract हो रहे हैं ना उसकी तरफ. So that's why the curly arrow is always from the electrons. Always from the electrons. ये याद रखो. Alright, so this attacks it. What would that do? भाई जब पहले ये curly arrow नहीं था, एक सिंपल मॉलिक्यूल आया था, तो उसने इलेक्ट्रॉन्स को पुश कर दिया था ना, तो उसकी वजह से ये इलेक्ट्रॉन्स जो हैं ये पुश हो गए थे, जिसकी वजह से यू गेट स्लाइटली पॉजिटिव एंड स्लाइटली नेगेटिव चार्जेस. ओके, बट व्हेन यू हैव अ फुल इलेक्ट्रॉन पेयर अटैकिंग इट, फुल इलेक्ट्रॉन पेयर जो इस पाई बॉन्ड का इलेक्ट्रॉन पेयर है, इट्स अटैकिंग दिस ब्रोमीन पॉजिटिव स्लाइटली पॉजिटिव थिंग, सो वो उसके इलेक्ट्रॉन्स को फर्दर पुश करेगा और उसकी वजह से यू विल गेट this moved on. So एक पेयर अटैक कर रहा है तो अगले पेयर को पुश अवे कर रहा है. उससे क्या होगा कि now this bond which had one electron from this atom, one electron from this atom, now this bond is between this one and one of these atoms. तो वो दोनों इलेक्ट्रॉन्स यूज अप हो जाएंगे to make this bond. So that is exactly what will happen कि हमारे पास let's suppose ये right वाला for whatever reason right वाले के पास ये ब्रोमीन आ जाता है. So these two electrons have been used to make the bond here. Okay, so this has diverted these electrons from this carbon towards this bromine. और ये दोनों electrons जो थे, ये दोनों इसको मिल गए. What happens to an atom when it gets one extra electron? Remember, one extra electron. क्यों? क्योंकि एक electron तो इसने पहले bonding में अपना दिया हुआ था, दूसरा electron इसको मिल गया, so one extra electron is what it got. This is a lone pair. And that carbon suddenly lost an electron. क्यों? उसने बॉन्ड बनाई हुई थी Now both of these were used to make bond with this bromine. So technically this bromine lost an electron here but gained an electron from here, and that is how it was able to make this bond. But this means this carbon lost its electron. Okay, and that is now a carbocation. Carbocations have their own thing, that whether they are more stable, less stable, whether they will sustain या whether they will go away, it depends on the stability of carbocation, which depends on कि किसके साथ attached है. लेकिन again we'll get back to that in a bit. अभी पहले हम इसको देखते हैं कि अच्छा carbocation बन गया. Now carbocation will get this lone pair to attack it. क्यों? जहां नेगेटिव होगा वो पॉजिटिव को अटैक करेगा. यहां पे नेगेटिव था क्लाउड में, उसने इस पॉजिटिव को अटैक किया. यहां पे नेगेटिव है, उसने इस पॉजिटिव को अटैक करना है. सो इफ यू आर एबल टू गेट द चार्जेस राइट, यू विल बी फाइन. ठीक है. सो अब दिस इज गोइंग टू अटैक दिस, एंड क्लियरली वी आर गोइंग टू गेट. देयर यू गो. Now this was a symmetric molecule. इसमें हमारे पास ये भी Br2 थे, दोनों same molecule, same atoms. These are both same situation. What if you have asymmetric situation? What if you have one carbon that is attached to more carbons and one carbon that's not attached to more carbons? Over there, we look at Markovnikov's rule. Markovnikov's rule basically बताता है ये कि कहाँ पे कार्बोकैटन बनने का चांस ज़्यादा है. सिंपल इज दैट. लेकिन मार्कोनिकोव्स रूल ना आसान बहुत है, तो चीजें आसान कर देता है वो. आपको एग्जाम में फौरन आप सोच लेते हो. मार्कोनिकोव्स रूल ये कहते हैं इन अ वेरी सिंपल वे, द थिंग विद मोर हाइड्रोजन गेट्स मोर हाइड्रोजन. ठीक है. दैट इज अ वेरी वेरी सिंपल केस ऑफ मार्कोनिकोव्स रूल. इसके अलावा मार्कोनिकोव्स रूल का एक और तरीका है सोचने का कि द थिंग विद मोर हाइड्रोजन गेट्स द थिंग विद लेस इलेक्ट्रोनेगेटिविटी. कि अगर हमारे पास यहाँ पे HBr हो और इसको हमने अटैक करवाना है इस सिचुएशन में, लेट्स डू इट. लेट्स सपोज मेरे पास ये यहाँ पे CH3 है और ये दिस इज द सिचुएशन. I have CH3 here and this is just hydrogen, this is just hydrogen. Okay, and now HBr का मैं इस पे अटैक करवाता हूँ. First of all, will it be HBr or will it be BRH? Which one? It will be HBr. Why? Again, remember, negative attracts positive. You already have slightly positive charge here, slightly negative charge here, because we already have a polar molecule. और यहाँ पर हैं इलेक्ट्रॉन. डबल बॉन्ड देखते साथ आपके ज़हन में ये इलेक्ट्रॉन्स आने चाहिए, और ये इलेक्ट्रॉन्स ऑब्वियसली किसी पॉजिटिव को ही पुल करेंगे. सो दैट्स व्हाई दिस इज गोइंग टू अप्रोच इट. और जैसे वो उसको अप्रोच करेगा तो यहां से अटैक होगा. सिंपल सी बात है, नेगेटिव अटैक्स पॉजिटिव. सिंपल एज दैट. इट्स सिंपली नेगेटिव अटैक्स पॉजिटिव. अच्छा जी, अब क्या होगा? दिस इज गोइंग टू ऑब्वियसली सॉरी आई गॉट अ मैसेज. ओके, या, so this is going to obviously attack this. Now what will happen next? When it attacks it, we have two options. Either this hydrogen makes bond with this carbon or with this carbon. Which one does it go to? So let's look at it through three different ways. First one, the simplest case of Markovnikov's rule. The thing with more hydrogens gets more hydrogen. Okay? So this carbon has two hydrogens. This carbon has just one hydrogen. Remember, I'm not counting these hydrogen because वो hydrogen नहीं है, वो methyl group है. As far as this carbon is concerned, it's attached to one hydrogen. This carbon is attached to two hydrogens. So Markovnikov's rule simply says the things with more hydrogen gets more hydrogen. Simple as that. ठीक है? So ये hydrogen इसको मिल जाएगा और कार्बोकैटन बनेगा इधर. ठीक है? एक तो ये तरीका होगा. दूसरा तरीका देख लेते हैं कि क्यों ऐसा क्यों हुआ. ये एग्जाम में हम कैसे इसको देखेंगे. द सेकेंड लेवल ऑफ मार्कोनिकोव्स रूल इज द थिंग विद मोर हाइड्रोजन गेट्स द लेस इलेक्ट्रोनेगेटिव पार्ट. द लेस इलेक्ट्रोनेगेटिव पार्ट. इन दोनों में लेस इलेक्ट्रोनेगेटिव कौन है? हाइड्रोजन. हाइड्रोजन इज द वन दैट इज लेस इलेक्ट्रोनेगेटिव. If you did not have hydrogen, but if you had something else, let's say this was a molecule between fluorine and bromine, then where will this reaction occur? On the bromine side. Because bromine has less electronegativity, fluorine has high electronegativity. In this case, the bromine will come here. Q, the thing with less electronegativity comes towards the carbon with more hydrogen. That's the second level of Markovnikov's rule, in case you have to deal with that. Obviously, हमारे पास तो simple cases हैं, HBr वगैरह हैं, तो ऐसा नहीं होगा. So H will come here. The third level of understanding why this happens here. Why does this carbon gets the hydrogen and this carbon does not? That has to do with stability of carbocation. To get to that, I need to tell you about two things in chemistry. One things are called activating groups and the other are called deactivating groups. Activating groups are the ones that have lone pairs that they provide. Activating groups have electrons that they provide in case something becomes a positive charge. What that does is it stabilizes the positive charge. अगर पॉजिटिव चार्ज बनेगा, एक चीज के ऊपर अचानक पॉजिटिव चार्ज बन गया, दिस सडनली लॉस्ट एन इलेक्ट्रॉन, बोथ ऑफ दीज कार्बन्स आके ये इलेक्ट्रॉन किधर जा रहा है, ये नहीं जाना चाहिए. देन अगर एक को हौसला मिल जाएगा ना कहीं से, then that one will stay. So the stability of carbocation depends on its neighbors. अगर हमारी जिंदगी में प्रॉब्लम आती है तो हम अपने आसपास के दोस्तों, फैमिली वगैरह से सपोर्ट लेते हैं. कार्बोकैटायन को अगर कोई प्रॉब्लम आती है तो वो अपने आसपास के ग्रुप से लेता है, और उस ग्रुप्स में दो तरह के हैं. ठीक है, कुछ है एक्टिवेटिंग ग्रुप्स विच सपोर्ट इट, कुछ है डीएक्टिवेटिंग ग्रुप्स जो जरूरत आने पे भाग जाते हैं. ठीक है, आई एम श्योर वी ऑल नो सच पीपल एज वेल. नाउ दीज एक्टिवेटिंग ग्रुप्स they will simply support it in case of it becoming a carbocation. उसने इलेक्ट्रॉन लूज किया ना, वो से कहते हैं कोई मसला नहीं, we will provide the electron if you need. वो इलेक्ट्रॉन देते नहीं है, they will provide electron if the need comes. ठीक है, so that's an important thing to remember. तो activating groups की लिस्ट है आपकी बुक में, you can just look at to that. Now these activating groups will stabilize a carbocation. उनमें एक सिंपल सा केस है हमारे पास मीथाइल का. मीथाइल अगर आपके पास होगा या एल्काइल कोई भी ग्रुप होगा, दैट विल बी एन एक्टिवेटिंग ग्रुप. सो एल्काइल ग्रुप्स विल ऑब्वियसली प्रोवाइड इलेक्ट्रॉन्स इफ द नीड कम्स. सो ये जो कार्बन है ना, इट हैज अ सेफ्टी नेट. इट हैज दिस एल्काइल ग्रुप प्रोवाइडिंग इट द पॉजिटिव इंडक्टिव इफेक्ट. सो दिस वन will provide a positive inductive effect, which is shown by this arrow on the bond. This is showing then in case of this becoming a carbocation, it will be a very stable one because this methyl will provide the support. But this one has no such thing. Hydrogen उसको बिल्कुल कोई support नहीं दे रहा. So then अगर ये carbocation बनेगा तो ये ज़्यादा देर बन नहीं पाएगा, which means कि it will not go through that. In reality, what happens is that it creates a carbocation for a very short amount of time, but then that carbocation shifts here because that is more stable. ठीक है? In reality, it is likely that some of these will try to make carbocation but fail, but eventually the stable carbocation always forms on the thing that has a more inductive effect coming towards it. And that is why the less stable thing gets the hydrogen first. उसमें हौसला ही नहीं है वेट करने का. This one gets the more electronegative part because it waits, good things come to those that wait. So यहाँ पर we will get the bromine with its electrons to attack the carbocation, and that is how we get this. Okay, so that is something you should know. Three levels of Markovnikov's rule. The simplest case, the thing with less hydrogen gets less hydrogen. Second, the thing with more hydrogen gets the less stable part. ठीक है? And the thing with less hydrogen gets the more stable part, more electronegative part, not stable. And third, the actual reason for that comes from the inductive effect and the stability of carbocation. If the carbocation is more stable, it will get the more electronegative thing. If the carbocation is less stable, it will get the less electronegative thing. Yes, Ryan, you're absolutely right in that. Yes, we will not say more methyls are attracted to it. We'll say they are at. Oh, you said methyl attached to it. Yes, that's right. If it has more methyl attached or any other activating groups attached, they will make it more stable. Okay, so that is electrophilic addition, and let me give you a basic question of that. Okay, ठीक है, we can work on the questions later on when they need to. अच्छा, next thing is oxidation. Oxidation का mechanism as such हमारे syllabus में नहीं है. It's simply that we need to know what those reactions do. So a simple case of oxidation is when the double bond in here is oxidized in presence of an oxidizing agent with some water. This is cold, which means room temperature, heat नहीं किया इसको. So what will happen is that the double bond will break, but not completely. Only the pi electrons will get involved. We don't need to go into the reaction mechanism for that. We just need to know that this will simply lead to both of them getting OH. And that's about it. Because the temperature is cold, we have an oxidizing agent, but that did not break the full bond. But if the same thing happened and we had an oxidizing agent which was hot and it was under the right conditions, then what will happen is that iski concentration is important, that this bond will simply break. So the full bond will break if it is hot and concentrated. Okay, so this is concentrated. And what that does depends on what it is attached to. So if this one is going to happen, then a simple carbon which is attached to just hydrogens, so ye hydrogen or ye hydrogen hai, then what will happen is that everyone is on their own. This will oxidize, this will oxidize, this will oxidize, everything will oxidize on their own. So kya hoga? Carbon oxidizes to make what? Carbon dioxide. Hydrogen oxidizes to make what? Water. So they will both do that. So every carbon for their own. So 2 carbon dioxide, 2 water. 2 water. Yep. So that is how this is made. Simple as that. Because every atom for themselves. उसको कोई अटैक करने, उसको कोई सपोर्ट करने वाला ही नहीं है, कोई मीथाइल ग्रुप एक्टिवेटिंग ग्रुप है ही नहीं. अच्छा, अगर मीथाइल ग्रुप हो, if there is an activating group, then it's not easy to let go of that. So if that is the case, let's say this has a CH3, and now I oxidize it, concentrated oxidizing agent and hot. So now when it obviously oxidizes, then this one will oxidize on its own because it doesn't have any support. So carbon dioxide from this one and these hydrogens, they will make water. Simple as that. But this one has some support. So what it does is it creates an alcohol. It breaks the bond, sure, but it does not let go of it altogether. ठीक है? तो ये alcohol नहीं बनता. It will form an aldehyde. Simply the bond breaks, and this part will make the bond with oxygen. Simple as that. The bond that it broke with carbon, it made with oxygen. Simple as that. Now, whether it can be further oxidized, yes. This same thing can be oxidized to make carboxylic acid, which we'll know later on. But for now, just remember that this makes aldehyde if you just let it happen right there. थोड़ी देर बाद it will make carboxylic acid if you let it oxidize further. So, because of the support or because of the bond between methyl group here, the activating group there, it can sustain itself and make bond with the oxygen. What if you have a situation where they had multiple groups supporting them? Or इसको भी CH3 कर देते हैं. So again, you look at every atom individually. This carbon can now oxidize without letting go of every other atom. So the left part, this will simply make the bond with oxygen by oxidizing. यहाँ पे oxidizing agent है, concentrated है, hot है. What about this carbon? Same thing. It will also do the same thing and make the bond with oxygen. Can this be further oxidized? This can, this cannot. ये नहीं कर सकता, ये कर सकता है. क्यों? हाइड्रोजन कैन गेट ऑक्सीडाइज्ड. तो पहले कार्बन ऑक्सीडाइज हो गया, अब ये हाइड्रोजन ऑक्सीडाइज हो गया, OH में कन्वर्ट हो सकता है. So that is something you need to know. For these, simply look at what are the other atoms attached to them. If it's just hydrogen, everyone is for themselves. But if it is methyl or alkyl groups, then they can support it and they can make aldehydes or ketones and all that. And aldehyde obviously further oxidizes to, this will do further oxidation, and you will end up with OH here. But the main part is simply how the oxidation happens and what the situation is. Okay, so that was oxidation. Any questions? Audio is echoing. Okay, hold on. I'll be back. Let me try to fix that. Alright, I hope this one is better. ये अब echo नहीं होना चाहिए hopefully. Let me know if that is still bothering you. If it still echoes, so please text me. Okay. With the cold one, it's simple that when somebody asks कि cold में वो क्या करता है, cold one is simple. Cold one doesn't do complete oxidation. हर atom को पूरी bond नहीं तोड़नी पड़ती. They just break the pi bond because the pi bond is going to take part in this reaction, and that's it. The sigma bond does not break. Okay, yeah. So this one is it. If you want to oxidize this further, yes, you can make aldehyde on this side and aldehyde on this side if you want to. But right now, as far as the oxidizing agent with presence of water is concerned, this is what will happen. Okay. Do tell me about the echo, please. All right, moving on. So now we know oxidation, and moving on, we have the nucleophilic substitution. Okay, so nucleophilic substitution usually occurs in halogen alkanes. We will represent them as Rx. The key thing about Rx is that you have slightly negative charge here, slightly positive charge here, because all halogens are more electronegative than the carbon that they have, which means that the bond will be polar. How polar depends on what one you have. So fluorine will make a really polar one, but bromine is not as polar as that one. Okay. Now, because of these, you already have slightly positive charge on the carbon. And slightly positive charge क्या चीज होती है? Slightly positive charge is a hotbed for nucleophiles to attack. ठीक है? So that's something you have to understand. And the second thing about this, so पहली चीज तो हमें पता लगी that you always have a slightly positive charge here, which is easy or which is a good place for these nucleophiles to attack. तो अगर कोई भी nucleophile होगा, nucleophile क्या होता है? Nucleophile has lone pair, nucleophile has negative or slightly negative charge. If one of these three things are there, it's more likely to be a nucleophile. So this nucleophile will obviously look for positives or any charge that is positive or slightly positive. And you already have it here. वो उसके अंदर inherently built in है. So अब क्या होगा कि let's suppose this carbocation is attached to some X. So यहाँ पे slightly positive charge है, यहाँ पे slightly negative charge है. If something with lone pairs wants to attack it, if some nucleophile comes in, so nucleophile aa gaya, this nucleophile has this lone pair, it will love to attack it because positive attracts negative. सारे reactions में positive attracts negative. So ये इसको attack करना चाहता है. But बात है, can it approach it or not? If this carbon is very crowded, if there are big atoms or groups of atoms around it, for example, यहाँ पे ये हाइड्रोजन बन जाते हैं, ये यहाँ पे ऐसे करके है, बड़े बड़े एटम्स इसके इस आसपास हैं, तो ये बेचारा इसको अटैक नहीं कर सकता, वो अप्रोच ही नहीं कर सकता. ठीक है, there's too many hurdles there. So in this case, this will have to wait. This will have to wait for this X to go away. Until that X goes away, nucleophile cannot come in. Now there are ways to make this go away, and they do happen. In that case, what happens is that first it detaches. जब ये जाएगा जगह बनेगी, and then the nucleophile will attack. Right now the nucleophile cannot approach it. It's very crowded. In this case, when it happens कि first it has to go and then the nucleophile comes in, we call it SN1. But if you had a situation where the same thing was attached to very simple situation like hydrogen atoms, or it was just hydrogen on one side and methyl on the other side, it's easy to approach this one, right? The nucleophile can relatively easily attack this one. Although इस वाले में तो हर तरह का attack हो सकता है, but let me just take it like this. Yeah, so this one is really easy to approach because the nucleophile can attack from here. There's a lot of space available, and because of this, the nucleophile will attack it at the same time while this is here. In that case, this will be an SN2 reaction. Okay. So that is something you have to know, that SN1 is when it's not easy to approach it, and SN2 is when it is easy to approach it. So that's the main idea. The idea is simply that is the carbocation accessible, or is the site where the nucleophile has to attack, is that accessible or not? If it is accessible, then that means it's not very crowded. It can attack right away. It doesn't have to wait, which means the reaction will happen right away, and it will happen in a one-step reaction. And if that is not the case, if it is too crowded, if it's not easily accessible, then this will be a two-step reaction. If it's a two-step reaction, why are we calling it SN1 and why are we calling this SN2? The idea is really simple. This does not tell me whether this is a two-step or a one-step reaction. This is simply telling me what does the rate of reaction depend on. The rate of reaction always depends on the slow step, right? And in the slow step, are there one thing whose concentration affects this, or is there two things whose concentration affects it? In this one, when the slow step happens, what is the slow step? The slow step is this going away. At that time, only this molecule matters. That how soon or how slowly does it lose this X so that the nucleophile can finally attack this. So it's only the concentration of this halogen alkane that matters. But in this case, two players are there. One is the nucleophile itself, which is also attacking, and one is this X, which is leaving. So the concentration of this one and this one both are important, and that is why the rate of reaction in the slow step वैसे है ही एक, but in the slow step, in this particular step, only the concentration of both of these will matter, and that's why it is SN2. This has two steps. The first step is slow when we wait for it to go away, and then the reaction attacks. Why? Because almost always you'll see the reactions between slightly positive and slightly negative charges are slower. The reaction between pure positive and negative charge is really, really fast. Okay? So now let's look at it. Okay, how does it actually attack? So do you understand why SN1 and SN2? We just need to focus on, is it accessible or not? Is the site where the reaction happens, can this be easily attacked or not? So let's get into it. So I'll start with, let's suppose, substitution of bromine with hydroxide. Okay, so I have a bromine here. I have a simple case of primary carbons. Okay, so this carbon, as you can see, is easily attacked from this side, from this side. Remember, not from this side. Why not? Because this bromine has a lot of electrons. It will repel any electrons coming towards it. So if the OH were to attack this one, okay, if the OH were to attack from here, then this bromine will simply repel it. It cannot allow it to come in. So that's why this OH has to find a place where it can easily attack it. So I'm just gonna focus on the lone pairs. So now this lone pair can attack it. Why? Because they already have positive and negative charges. Alright, so now this can attack it. Usually we just show one lone pair, we don't show all, no particular reason for that. We just want to focus on the part that's taking part in the reaction, just to show how the reaction is happening. So OH has a negative part, lone pairs that can attack it. Although it still has 3 lone pairs, but we only work on one, which is the one that's actually reacting. So why did it not come from here? Simple. This is going to repel it because it has slightly negative charges already. It doesn't allow it to come in. So why does it attack from here? Because the atoms are really small. It's easier approach. वो आराम से उसको attack कर लेगा. And now this reaction, this attack happens while the bromine is here. And as it comes in, this bond goes away. This is a pattern that we saw. We saw over here as well that when this bond was created, this bond was pushed away. Exactly like that, when this is attacking it, when the attack happens, an existing bond with a similar species is pushed away. So that's exactly what happens. A nucleophile comes in, the other nucleophile is pushed out. So we get the next step where this carbon is in a like an intermediate step. There is a bond with this bromine, there is a bond with this OH, but it's not really a permanent bond. We talked about it yesterday at the start of the lesson yesterday, that how does this occur, and you still get like 2 hydrogens making these bonds. Okay, so I can make like a wedge here, and just to show how the reaction is happening. Okay, so there you go. This is all of it happening in an intermediate state. This is not a product, it's just an intermediate. So this whole thing is an intermediate. And now finally, one of these is going to be let go and the other is going to stay. And uski wajah se what we will see is that, wait a minute, how did that hydrogen get all the way over there? That shouldn't be happening. Sorry about that. This shouldn't be happening. The location of hydrogen doesn't change. It's simply this. Yeah. Okay. So now this creates. Here you had Br, right? Now you don't have Br there. The OH has taken its place. But notice that I did not put OH here. OH attacked from here, so OH stays on the top side. So the orientation does change a little bit when you do these reactions. आप ये नहीं लिखना कि यही bromine वाली bond पे यहाँ पे OH आ गया. Don't do that. Even though it doesn't matter, this is not a 3D formula, but still it's useful to understand that whenever this kind of situation happens, because the new nucleophile comes from the opposite side of the existing nucleophile, the orientation changes a little bit. Okay, so the molecule will not have bromine going from the same side where the OH comes in. It's always from the opposite sides. This is like a 2D diagram. Here it doesn't matter, but in a 3D formula it does matter. Okay, so that is SN2. Does everybody understand this? Any questions here? Yes, Ryan, you're absolutely right. We just made alcohol here. Yes, and we do need water to provide us with the excess OH and all that. The situation depends how you're doing it. Sodium hydroxide in ethanolic condition won't do it, but sodium hydroxide in aqueous condition will do it. Okay, what if this carbon was not easily accessible? What will happen in that case? Yes, Saeed, what did you want to ask? The Br then makes HBr. It depends what is available. If there is sodium ions available, then Br will attack sodium ions and make sodium bromide. If sodium is not available, or if hydrogen ions are more prevalent, more excessive, then it will simply react with them and make that. In some cases, it can also react with water, create new H positives. And then, so for example, this Br, which is over here, if there was sodium ion available, it will react with that. Potassium ion available, it will react with that. But what if there was only water ion available, water molecule available? Then this Br will go there. Water has slightly positive and slightly negative charges, obviously. So this will create a bond with this one because it will simply attack it. And that will push the electrons here, and you will get a new OH ion made, okay, and HBr made. So depends in what environment the reaction is happening. So this is usually what happens, by the way. This is usually the one that happens. And can you tell me why? Why is it that even though sodium ions were added, they still end up making more HBr, not more sodium bromide? Why is that? Well, obviously because it's happening in aqueous environment. There's lots of water molecule available. The sodium hydroxide was added in a very small amounts. It's mainly water molecule that is available, so that's why it makes HBr. Moaz, I don't understand your question. How does the intermediate state happen? I mean, what do you mean? Because it attacked it while this bromide was here, दोनों nucleophile एक time पे उसके साथ attached हैं, that is why the intermediate state happened. If it waited, अगर ये wait करता कि ये bromide छोड़ के चला जाए, if it waited for that to go away, then it won't make an intermediate like this one. It will make a different kind of intermediate. But because both the nucleophiles are attached to the same site at the same time, that's why we are getting an intermediate that is like this one. Does that answer your question? We don't have a carbocation formed right now. Okay, so don't think that this is a carbocation. There's no carbocation here. Because carbocation तो तब बनता ना अगर उसको वो जगह देता करने की, वो उसने उसको दी नहीं space. Alright, let's move on to the next one. But if you have any question, feel free to ask. The whole point is to answer your questions here. Okay? This is SN2, yeah. This is SN2 because the concentration of the halogen alkane and the nucleophile, both of them determine which in the slow step, which is technically the same step. If you want to call it transition, yes, you can call it that. We can call it transition state. Yes, absolutely. Moaz, I've already answered that like 10 minutes ago, so you can just review it. It depends on whether the carbon is easily accessible or not. If the carbon is easily accessible, then the nucleophile will not wait for the X to go away. But if the carbon is not easily accessible, like right now it's very crowded, the only place where the nucleophile can attack it from this side, but cannot do that because this will simply repel the nucleophile. So nucleophile ने यहाँ इधर से आना है या इधर से आना है और इस साइड पे जगह ही नहीं है तो इस वजह से it will wait. So this is SN1. It will first wait for it to leave. But यहाँ पर nucleophile इधर से आ नहीं सकता. Nucleophile इधर से आएगा या इधर से आएगा. Most likely इधर से आएगा. And because of that, because there is a lot of space available, it can simply attack it while the X is there. And that's why this is SN1 and SN2. Okay? The transition and intermediate state right now doesn't really matter because at the end of it, we are getting to the final product anyway. But transition state is one that is does not stay for a long time. Intermediate state can be considered कि sometimes intermediate steps happen कि वहाँ पे एक stable product बनता है and then you move on to another step, another stable product. So if a stable product exists, we usually call it an intermediate state. But if a stable product is not made during the reaction steps, we call it a transition state कि वो वहाँ पे रुकता नहीं है ज़्यादा देर. Intermediate में वो उस पे it can stay for a while over there. So intermediate stage is when it is making a stable product, relatively stable product, and transition state is where the product does not stay. It's not that stable anymore. Okay, but that's not something you lose marks on. All right, now what if the carbon with the positive, slightly positive charge was not easily accessible? What will happen in that case? So in that case, let me take an example of this is chlorine, for example, and this is CH3, this is CH3, and this is C2H5. Now, while we have just written them here, you have to understand this is the geometry of these things. This is the shortest side of this carbon. This, and this, they are long areas. वो ऐसे फैला हुआ है पूरे का पूरा और वहाँ से न्यूक्लियोफाइल के आने का चांस बहुत कम है. So for example, if OH were to approach it, then यहाँ से वो आ नहीं सकता. If it tries to come from here, what's the problem? The chlorine will repel it. So if it tries to come here, chlorine will repel it, it will go away. If it comes from here, chlorine will repel it, it goes away. If it tries to come from here, it is too crowded already. There's too many atoms here. So that's why it cannot attack the carbon anyway. वो जितनी मर्जी कोशिश करे, it's not getting to the carbon. So that's why it waits for this chlorine to go away. So then we have to find a way to lure this chlorine out. वो chlorine को हम कैसे निकालते हैं? We use H positive ion for example. वो chlorine के साथ bond बनाएगा, chlorine उसके पीछे पीछे छोड़ के आ जाएगा उसको. ठीक है? So there's different things that allow us to do that. So whatever that happens, this bond has to break and this chlorine has to go out. However that happens doesn't matter, but it has to. Okay? And we say that that is also because this carbon will now make a positive, a stable carbocation. If this tried to make a stable carbocation, it will fail pretty much because it has just positive inductive effect from this side. But this has positive inductive effect from here, here, here. अगर वो कार्बोकैटन बन भी जाता है, अगर क्लोरीन उसको छोड़ भी जाता है, वो कहता है ठीक है, I'll handle, वो stable रहेगा. So that is why this is more likely to do that. So this will form a stable carbocation और क्लोरीन को वो कहेगा कि जा अपनी जिंदगी जी. Now the chloride is obviously going to go away. It goes away and the OH with its lone pair comes in. It steps in and it does attack it. This is a really fast step. क्यों? Full positive, full negative charge. जब full positive, full negative charge होगा तो reaction हमेशा बहुत तेज होगा. Partially negative पे depend किया तो reaction slow होगा. Which is why this is a slow step. That's a fast step. And then it creates OH here. Again, orientation की जहाँ पे बात करें, it's important to know that in this reaction, OH is coming exactly where the chloride left from. Okay, so that is how it attacks it, and that is this chloride will go away. If there's sodium ion available, it will react with that to make sodium chloride. If water molecules are available, then it will make HCl and create a new OH from the water molecule, just like we saw earlier. ठीक है? So that is how this reaction occurs. Any questions? So again, it all depends on whether the carbon is easily accessible or not. But the technical reason for that is whether the carbocation that will form, will it be stable or will it not be stable? If the carbocation that forms will be stable, वो कहता है कि ठीक है, मुझे कोई जल्दी नहीं है substitution करने की, I'll just wait for it to go away. But अगर carbocation stable नहीं है, तो वो अपनी ऑप्शंस खुली रखता है, वो दोनों को एक ही टाइम पे इंगेज करता है और दोनों के साथ फिर फाइनली देखता है उसने क्या करना है. ठीक है? So this one is a tertiary carbocation. This is pretty stable, yeah. Okay. Any questions in this one? Okay, moving on, we have elimination reaction. Why do we want to have another nucleophile while we have another nucleophile? Good question. It's not a silly question. Nucleophiles can make new products, and one nucleophile can be more reactive than the other. So it's kind of like, याद है हमने metals में displacement reaction देखा था कि for example, if I already have let's say iron oxide and I bring in carbon. So carbon can displace iron and make carbon dioxide, which is what we do in blast furnace, right? Similarly, if I have aluminum oxide और वहाँ पे हम sodium के साथ उसका reaction करवाते हैं, तो more likely that sodium will simply replace it and make sodium oxide and aluminum will go out. But of course, we don't do that in industry because it can be a very expensive process. Similarly, copper oxide की जब हम reduction करते हैं कार्बन की रिडक्शन करते हैं या हाइड्रोजन की रिडक्शन करते हैं. सो हाइड्रोजन कम्स इन, मेक्स वाटर, कॉपर मेटल हमें वो मिल जाता है. All of this is something more reactive displacing something less reactive. Over here, it doesn't have to always be the same order because these are very like mobile ions और इसमें हमेशा एक fixed rule नहीं होता. But there are roles to play. OH ion is much smaller. Chloride ion is relatively bigger. Similarly, अगर bromide है तो उससे तो OH is much much smaller. OH has more charge density. So in a way, it is more पैक्ड फॉर नेगेटिव चार्ज. तो वो उस कार्बन को इजीली ज़्यादा अट्रैक्ट कर सकता है. ब्रोमाइड उस तरह से अट्रैक्ट नहीं कर सकता. सो दिस काइंड ऑफ सब्स्टिट्यूशन दैट हैपन्स, वी डोंट कॉल इट डिस्प्लेसमेंट, वी कॉल इट सब्स्टिट्यूशन. डिस्प्लेसमेंट इज यूजली केप्ट फॉर जो हमने आपको पहले मैंने एग्जाम्पल्स दी. सो द रीजन वाई दिस हैपन्स इज सिंपली वन थिंग डिस्प्लेसिंग द अदर वन बिकॉज दे कैन. दैट्स इट. वो उससे ज़्यादा रिएक्टिव है या वो सिचुएशन ऐसी बन गई है कि वहाँ पे वो कर सकता है. ट्राइंग न्यू थिंग्स, नो पर्टिकुलर रीजन most of the time. Major minor products वाला हमने थोड़ी देर पहले देखा था. Major minor products में you just need to understand the Markovnikov's rule that the major product is always considered through the Markovnikov's rule. वो जो 3 categories मैंने आपको बताई थी. Minor product वो होगा जो उसमें follow नहीं करता. It's simple as that. Minor product की ratios के वो किस percentage में बनेगा वो हमारे A levels के syllabus में नहीं है. वो IB में भी नहीं है बल्कि वो तो या फिर वो बाद में आप पढ़ोगे. But we don't study that in A levels or IB. The more stable carbocation will form the major product. Absolutely, that is always correct. Yes. All right. So let's move on to the one where. So this one is done. We already know how this will occur. This chloride is going to go away and make some product depending on what's available. Sodium ions available, it will make sodium chloride. Usually that's not the case. Usually we have a lot of water molecules, so it makes HCl. Creating new OH in the process, and those OH continue with this process. Okay? So that is going to happen. Next reaction we have is elimination reaction. Elimination is a pretty straightforward reaction. What happens is that the bond breaks and a double bond is created. So for example, I have this, and let's say I have Br here. Then what will happen is that the bond will break and in presence of the right condition, obviously sodium hydroxide ethanolic hota hai hamare paas. So what it will do is it will basically allow this to let go of HBr. So HBr will be formed, and what happens here, this H for example goes away, this Br goes away, they make a bond between each other. तो जहाँ से वो जाते हैं उनके बीच में आपस में बॉन्ड बन जाती है. It's simple as that. The exact mechanism for that is not in A-level syllabus. You just need to understand how the elimination reaction happens, and that is it. So elimination reaction can always occur in presence of ethanolic sodium hydroxide. Why ethanol helps? Why sodium hydroxide is able to do that, or KOH is able to do that? We don't need it for now. Okay? So we don't need to worry about it. Next question is it possible to substitute OH with anything? हमने यहाँ पे तो OH सब में ऐड करवा दिया ना. इज इट पॉसिबल टू रिप्लेस OH विद समथिंग एल्स? येस, इट इज़ पॉसिबल, बट अगेन इट डिपेंड्स ऑन द कंडीशन दैट यू हैव, एंड यू कैन ऑब्वियसली गो बैक फ्रॉम OH टू Cl. मैं Cl इसमें ला सकता हूँ. इट्स वेरी ईजी, and that obviously depends on this reacting with HCl, for example, this reacting with HBr, for example. Okay, so that will reverse this whole process. So it depends on the conditions. Organic is very versatile. You can make new things from almost anything, and that is why it depends on the right conditions. Here we had sodium hydroxide, water molecules, all of them providing a lot of an endless supply of OH minus. So the chloride was being removed. If you added HCl instead, chloride will start to be added. So it depends on what you have. Why do we do reflux? Because reflux does not allow these things to go away. These things are usually volatile. अगर आप इसको हीट करते हो तो वो they evaporate and leave. Reflux allows us to keep the reaction going without a lot of pressure building up. क्योंकि देखो, अगर मैं उसको कवर कर दूँ, मैं उसे कहूँ कि जाने नहीं देना मैंने, so it will happen that the gas will produce and they will evaporate and then they will just explode because you have a lot of pressure building up. But reflux allows us to just let them go for a while, remove the extra heat that they have, pressure build up नहीं होता, वो cool down होते हैं, वापस आ जाते हैं. So that is why we do reflux. If we want a reaction to keep going without things leaving out, without things evaporating or just being volatile and going away, while doing it in a safe environment, we do reflux. Okay. Alkyl halide with ammonia. Same thing. Alkyl halide with ammonia क्या होगा? हमारे पास amine create हो जाएगा. ठीक है. So that's also pretty straightforward. Uh, Nothing in particular over there. I'm not going through all the reaction right now. I'm just going through the reaction. इनके mechanism आपको आनी चाहिए. Okay. Yeah. We have seen this one. Elimination. Yeah. We don't need to go into the esterification process because that's again very similar to this one. No mechanisms required there. Again, the reactions are there, which we will do when we do those chapters in particular, but mechanisms उनके हमें से Watson नहीं पूछता. Okay, let me see what's the next mechanism. Yeah, the next mechanism should be nucleophilic addition. We have already seen electrophilic addition. Now let's look at nucleophilic addition. So let's try looking at a ketone. So nucleophilic. Okay, so with nucleophilic addition, what we need to understand is how does this happen? Ali's question is why does HBr form in the elimination reaction and not NABR? I've already answered that because there's a lot of water molecules available, those water molecules will provide protons and make HBr. There's very little amount of sodium ions available, and that's why it doesn't create that in a large quantity. Why do we do reflux and elimination? If you'll do reflux anywhere you have products that are volatile or you have reactants that are volatile that are leaving out the reactions vessel, we don't want them to go away, we will use reflux there all the time. So it's not specific to elimination. In any reaction where these things are volatile and they're leaving out and we don't want them to do that, we will do reflux. Okay, so let's say I have this situation. What is happening here? I have slightly negative charge here, slightly positive charge here. I have something, let's suppose either hydrogen है इधर कुछ methyl कर देते हैं. Okay, so we have an aldehyde and I want this to react with HCN. Okay, so what will happen? You have to understand how this bond behaves in this situation. What is HCN doing? HCN is providing us with nitrile, CN minus. What is that CN minus gonna do? So there is a triple bond here, there's a lone pair here. Many students make a mistake that they think that the lone pair is coming from nitrogen. Here, the lone pair is coming from carbon. Okay, so remember this. And you have a negative charge here. So this lone pair is looking at this because positive negative charges attract karte hain. So this wants to come here, but it cannot do that because there's a lot of negative charge built up here. So how does this negative charge come into play and how does this happen? Really straightforward. First of all, this will attack it. Okay? Why is this reaction happening? And why wasn't it able to react with chloride? Because chloride जो है वो इसको repel कर रहा था. क्या ये repel नहीं कर रहा? ये कर रहा है repel. But it's the direction that matters. कि ये इसको इस direction से आ रहा है. ये भी छोटा सा molecule, छोटा सा atom है. ये भी not that big. Chloride was much bigger. Anyways, so the idea here is that this one is able to attack this one. Why? Because there is lots of negative charges which are attracted by oxide, and this is negative charge that's attracted by this positive. So this has a high electronegativity. This can keep the bond towards itself. Already यहाँ पे positive charges create हुए हैं. So ये जो negative charges हैं, ये इसको attack करते हैं. Simple as that. The lone pair wants to attack this positive charge. Okay. So ये nucleophile ने इसको attack किया. So far, this is very similar to what we have studied earlier. Nucleophilic substitution में भी तो यही हो रहा था. That in lone pair was attacking a positive center. That's exactly what's happening here. But here the things change. This now makes the bond with this CN. Easy as that. But what happens to this oxygen and the double bond that it had? obviously this carbon, even if it's being greedy, even if it wants to make bond here, वो 5 bonds तो नहीं बना सकता. So this has to let go of one bond. So the oxygen pulls the electrons here. Have we seen this before? Of course. We saw it in alkenes. यहाँ पे हमने देखा जैसे ही ये इसके पास आया, इसने बॉन्ड ने अपने इलेक्ट्रॉन्स उधर पुश कर दिए. फिर हमने इसको यहाँ पे देखा, जैसे ही ये इसके पास आया, इसने अपने इलेक्ट्रॉन्स पुश कर दिए. ऑब्वियसली एक चीज़ आ रही है तो दूसरी चीज़ को जाना पड़ेगा. और यहाँ पर भी हमने देखा है कि व्हेन इट कम्स हेयर, one of the bonds here. The difference between what we saw earlier and what we're seeing right now is that earlier we had just one bond between carbon and the other atom or the other whatever group we had. Here we have double bond. So that double bond, only one of the bond breaks, the other bond does not break. That's the only difference in what we saw earlier, what we saw now. Abhi tak underlying reasons wahi hai. It's the same negative attacking positive. It's the same lone pairs coming in. It's the same one bond coming in, one bond going away. The only thing that's changed is now that we have a double bond. So this carbon simply retains one bond with oxygen, and this oxygen now has a lone pair with a negative charge of its own, which means that now this oxygen is a hotbed where positive charges can come in. अब ये positive charges आएंगे या stable molecule को ये खुद attack करेगा. It depends on what you have. So do you notice that this lone pair was able to attack this? So why wouldn't this lone pair attack anything else? It does. That's exactly what happens. ये एक stable molecule था ना, इसको इस lone pair ने attack कर दिया, अच्छे खासे stable molecule को attack कर दिया. Just like this one is going to attack another molecule. So let's suppose मेरे पास एक और HCN पड़ा हुआ है. It will simply attack it. Slightly negative charge, positive charge है, slightly negative charge है. ये इसको attack कर देगा. Simple as that. तो अब हमारे पास यहाँ पे क्या बनेगा? This will create OH and a new CN, and the reaction keeps on going. अब ये चीज़ हमने पहले देखी थी, ऑफ कोर्स हमने देखी थी. जब हमने फ्री रेडिकल सब्स्टिट्यूशन में देखा, हमने देखा कि रेडिकल जब मॉलिक्यूल को अटैक करता है तो उसके बाद एक नया रेडिकल बनता है और वो रिएक्शन कंटिन्यू करता है. हमने देखा कि न्यूक्लियोफाइल जब सब्स्टिट्यूट करता है दूसरे न्यूक्लियोफाइल को तो वो नया न्यूक्लियोफाइल बनता है जो जाके किसी के साथ रिएक्ट करता है. हमने यहाँ पे भी यही देखा है कि आपके पास जब ये लोन पेयर आ गया है, दिस इज अ न्यूक्लियोफाइल, दिस विल अटैक अदर स्टेबल मॉलिक्यूल्स एंड मेक दिस. इफ स्टेबल मॉलिक्यूल्स आर नॉट अवेलेबल तो रिएक्शन खत्म हो जाएगा. कैसे? इट विल सिंपली अटैक वट एवर आयन इज अवेलेबल. कैटाइन पड़ा होगा वो उसके साथ रिएक्ट करेगा, काम खत्म. बट अगर दूसरा मॉलिक्यूल है तो वो उसके साथ रिएक्ट करेगा. यहाँ पे क्वेश्चन ये आता है कि वाई डोंट वी सिंपली रिएक्टेड विद H from the HCN earlier on? Why don't we do that? Why do we show okay it is reacting with another stable molecule? So for that the answer is really simple, that collision theory yaad hai. The reaction happens because of collision between the reactant particles. Imagine you have a full vessel जिसमें you have many different moles of these molecules. What are the chances that the proton that this let go earlier is going to be the proton that attacks this one? What are the chances? The molecules and the atoms and ions, they are like there's billions upon billions of them. What is the chance कि एक वो प्रोटॉन जो इसने छोड़ा था वो वापस आके इधर रिएक्ट करेगा compared to the all the billions of stable molecules being there? Of course the highest probability is of this reaction happening, that it goes and reacts with a stable molecule. The chance of that proton coming back is ridiculously low. ठीक है? So that is why this is the one that we write. We don't write the one with stable molecule, stable cation. Will that happen? Yes. Does it happen? Yes. Does it happen as frequently as this one? No. Why? Probability. इसके होने का chance ज़्यादा है. There's more HCN molecules compared to protons. That's why. I hope that explains it for you. I hope कोई इसमें कोई issue तो नहीं है. If you do, तो please ask me. Alright. So again, over here, what's happening is that you have CN attacking this, pushing the bond away. तो अभी तक जितने भी हमने रिएक्शन मैकेनिज्म देखे हैं उनमें हमने सिमिलर ट्रेंड्स देखे हैं. एक नेगेटिव चीज़ आती है, पॉजिटिव पे अटैक करती है, दूसरी नेगेटिव को पुश आउट कर देती है. अगर उसकी एक बॉन्ड हो तो वो टूट जाती है, दो बॉन्ड्स हो उनमें से एक टूट जाती है, और जब वो चीज़ पुश आउट हो जाती है उस पर लोन पेयर आता है. वो लोन पेयर जो है वो किसी कैटायन को, किसी स्टेबल मॉलिक्यूल को, किसी स्लाइडली पॉजिटिव चार्ज को अटैक करता है और वहाँ से वो जो भी बना सकता है वो बनाता है. वी सॉ दैट हेयर, we saw that in the previous two examples, and we saw a similar version in free radical substitution. Underlying idea is the same. Positive attracts negative, and that's about it. कोई इसमें नई बात नहीं है. Okay, so I hope you're able to make these connections. If you're able to make these connections, you'll be fine. If not, I would suggest कि इसी वीडियो को थोड़ा सा फास्ट स्पीड पे दोबारा देख लें. Try to see the similarities between these reactions, and then try to see कि वो differ कैसे करता है और क्यों एक जगह पे आप देखोगे कि यहाँ पे न्यूक्लियोफिलिक सब्स्टिट्यूशन होगी या इलेक्ट्रोफिलिक सब्स्टिट्यूशन होगी या इलेक्ट्रोफिलिक एडिशन होगी या न्यूक्लियोफिलिक एडिशन होगी, कौन से होने का चांस ज़्यादा है वो आपको आराम से पता चल जाएगा बेस्ड ऑन व्हाट यू हैव ओवर देयर. ओके, so that is the end of these reaction mechanisms. If you, this is all for AS. For electrophilic addition and all that, we will review the A2 wala syllabus once we're done with this. So I will get back to you on that. Any questions? If no, then here's what you have to do. You have to first review this from the book or notes or जहाँ से भी आप उसको पढ़ते हो. But second and more important step, you have to go to the past papers. Random past papers खोलो. AS के paper 2 for example आप खोलते हो. Just look for the question where they ask you for a mechanism. एक rough copy पे mechanism draw करो उस particular example के साथ. Move on to the next paper. Look for the question that has reaction mechanism. Draw that out. Do it for as many papers as you can. ठीक है? Try to do it today sometime ताकि आपका fresh हो और आपको पता लग जाए कि ये जो चीज़ आपने अभी पढ़ी है ये वहाँ पे कैसे अप्लाई होती है. It is very important that you do this today before our next class tomorrow. Tomorrow we will do some reactions in detail. हम देखेंगे कि कौन कौन से reaction कैसे होते हैं, and we'll also look at some A2 reactions. Wait a minute, I can't have class tomorrow. I have to go to the reunion. मेरी यूनिवर्सिटी की reunion हो रही है, so I'm gonna go there. Will I solve past papers? Yes, I will solve past papers, but I think it's important that we review the concepts first. So tomorrow I will not do a live stream at this time because I have to go. But day after tomorrow, when we come back, we will review A2 reaction mechanism, and we'll also do some questions. We'll also review some reactions for the rest of the syllabus. All right. So that's it for today. Thank you so much for watching. I will see you in the next class. Do like, share, subscribe and invite your friends. I hope this was helpful. See you in the next time. Bye.